Hello, this is the video abstract for the research article, A Characterization of Higher Torsion Classes, which was published recently in Forum of Mathematics, Sigma, by Cambridge University Press. This paper has been authored by 6 people: Jenny August from the University of Glasgow, Johanne Haugland from NTNU in Norway, Karin Jacobsen from the University of Aarhus, Sondre Kvamme from NTNU, also in Trondheim, Yann Palu from the University of Amiens in France, and myself, Hipolito Treffinger, from the University of Buenos Aires in Argentina. Our motivation for this work stems from the representation theory of art in algebras, and it can be framed in the study of 3 main areas of research, which are, on the first, higher homological algebra, which is the study of certain categorical structures that generalize usual categorical structures studied in representation theory. Such categorical structures are, for instance, the abelian categories, d+2 angulated categories, or even dx angulated categories. Torsion classes have been present in representation theory for many years now. They were first introduced by Dixon for general abelian categories, but in the past 50 years have been studied from the relationship with certain particular objects within the categories. And in particular, they have a strong link with tilting theories or tau tilting theory, just for name an example. Finally, combinatorial representation theory is the study of the representation theory of certain algebras that can be described combinatorially. That the objects between the objects in the composable objects, maybe all objects or maybe only certain in the composable objects, can be described combinatorially, and even the maps and extensions between those objects can be described using combinatorial tools, and that's what I call here combinatorial representation theory. So, as I said, our work can be framed within higher homological algebra, and in order to do that, let me remind you what is a D-cluster tilting subcategory. A D-cluster tilting subcategory, this is a notion introduced by Yama, is a subcategory M of some abelian category that is rigid. So once you fix a positive integer d, this category M is rigid. So if you take any two objects in M, there are no extensions between them, no ith extensions for I between 1 and d-1, and it is maximal with respect to this property. Actually, you start studying the notions and the properties that the D-cluster tilting subcategory has, and Gustavo Hasso came up with the notion of what should be a D-cluster tilting a D-abelian category, and he actually defined give the axiomatic definition of D-abelian categories and showed that actually every D-cluster tilting subcategory of some abelian category is indeed a D-abelian category. Very recently, in 2 independent works, one by Ebrahimi and Nazar Isfahani, and another by Sondre Kvamme, they have shown that every D-abelian category actually can be always seen as the D-cluster tilting subcategory of some abelian category that you build with that purpose. All right. Now, what are torsion classes? Torsion classes actually are 1/2 of a torsion pair. What is a torsion pair? Torsion pair is a pair of subcategories of an abelian category A, such that for every object X in your abelian category, there is one exact sequence, which actually you can show that is unique up to isomorphism, such that the subobject of that of X in that exact sequence belongs to the torsion class, and the quotient of that inclusion is actually in the torsion-free class. And the second condition is that there are no morphisms between any object in T from the torsion class to any object in the torsion-free class. Actually, when A is an abelian length category, which would be an hypothesis that we will assume throughout this video, then the subcategories of an abelian categories which are torsion classes are exactly those which are closed under extensions and quotients. Now, so you have the abelian categories, you have torsion classes. What is a d-torsion class? Well, a d-torsion class is a subcategory of a d-abelian category such that for every object M in the d-abelian category, this object M has a subobject UM in this d-torsion class, such that the d-co-kernel of this inclusion satisfies a certain homological property, a certain homological exactness that actually recovers the notion of d-torsion classes that were defined as before by Dixon. Now, what is one can show actually that every time you have a d-torsion class U inside a d-abelian category M, that it is in turn a d-cluster tilting subcategory of some subcategory A, then this d-torsion class U is the intersection of some torsion class T in A and the d-cluster tilting subcategory M. This will allow us actually throughout the paper that you will be reading, will allow us to actually use a lot of tools of classical torsion classes to study higher torsion classes. Now, we said that torsion classes in abelian categories are those subcategories which are exactly closed under extensions and quotients. But one needs to be very careful when try to say what it is to be closed under D extensions in a D cluster tilting subcategory and a D abelian category, because the building blocks, the D extensions, the minimal D extensions that you could get are actually very long and will allow you to introduce anything you want if you bring this, if you study closeness under the extension or the quotients naively. So one can come up with a appropriate notion of closeness under the extensions and the quotients, and with these appropriate notions, which are very natural, as you would see if you read the paper, we can show our main theorem of the paper that says that a D-cluster tilting inside a D-cluster tilting subcategory of an abelian category A, a subcategory U is a d-torsion class if and only if it is closed under D extensions and D quotients. So one recovers this result by Dixon of subcategories of abelian categories inside abelian length categories. Now, it is important to remind you that actually d-torsion classes have, so every d-torsion class induces a subobject U inside any object M in M, right? And in order to show the existence of this subobject, we showed actually an intermediate result, which is this proposition that I want to highlight here, that says that every map in a D-cluster tilting subcategory factors in the following way. So if you have any map, it factors by F1 and F2, where F1 is a composition of weak co-kernels on the one hand side, and in the other, we have a monomorphism. So actually there is, we needed to show, and we showed actually, that when you are working in a D-cluster tilting subcategory inside an abelian length category, there is some kind of factoring through the image that is very, very important and that might be useful for you if you're working with higher torsion classes or higher homological algebra at some point in your life. Now, an important consequence of this, of our main result, is that if you take a D-cluster tilting subcategory of some abelian category A, then all torsion classes form a poset, naturally with inclusion, but this poset is actually a complete lattice. And the mid is given by the intersection. Now, also we wanted to understand some higher torsion classes in algebras which have been studied combinatorially. The most famous example of a family of algebras that have been studied combinatorially are called Auslander algebras. And Auslander algebras have, one can show, Yama have shown, that have a D-cluster tilting subcategory that can be described combinatorially. And later, Opperman-Thomas, and also Hasso, Kilshammer, Sadurakis, and Kvamme have shown that both morphisms and extensions between those can be described combinatorially. And starting with that, we were able to show when a set of indecomposable objects, so the additive closure of some indecomposable objects, actually is a d-torsion class inside the cluster tilting subcategory of a higher Auslander algebra. With this, we actually can give you algorithms to find the minimal d-torsion class containing any set of indecomposables that you gave us. And also, we can find all the d-torsion classes within the abelian category, the cluster tilting subcategory inside higher Auslander algebras. And this allowed us to build this particular table in which you can find for any given d and given n how many d-torsion classes there are. It is worth noting that these two algorithms were actually implemented by Karin Jacobsen, and you can see it in this following link. Finally, we not only get all the torsion classes, but we can also, in this algorithm that Karin did, is an algorithm that implemented by Karin, give you also the poset of these torsion classes. And with this poset of torsion classes, we realize that these lattices of d-torsion classes are not semi-distributive. There is a big theorem by Thomas and collaborators that all torsion classes inside an abelian module category of an algebra is actually semi-distributive. The answer here is that this is no longer true for higher torsion classes. Finally, I would like to mention that there are two other families of algebras that can be described combinatorially, that have the cluster tilting subcategories which can be described combinatorially. These are higher Nakayama algebras, and which comes from two different types, from type A, and for those we can also describe combinatorially higher torsion classes, and also for higher Nakayama algebras of type A infinity. Infinity, for those, we also have a theorem telling you when a subset of indecomposables, and if you take a subset of indecomposables, you close under direct sums, then you get a d-cluster tilting, a d-torsion class in this module category. Okay, this is all for us. Thank you very much.